So this is lecture RS-4. In the first part, 4a, we're going to be talking about how oxygen is carried in the blood, talking about hemoglobin and the oxygen-hemoglobin dissociation curve. In B, we'll talk about carbon dioxide in the blood, how it reacts with water in the bicarbonate buffer equation, which you may have already seen in Lab 20, and then how CO2 is distributed in the blood. And then finally, in part C, we'll talk about the regulation of ventilation, what our body uses to determine how rapidly we need to breathe. Today we're going to be talking about how oxygen is carried in the blood. So when we've talked about oxygen in blood before, we mentioned the concept of hemoglobin. Let's talk about why hemoglobin is necessary. So oxygen does dissolve in water, and plasma is mostly water. But oxygen solubility in water is not very high. The amount of oxygen that can dissolve in the plasma alone, if we had no hemoglobin, is relatively small, and it's not nearly enough. It's something like 10% of what our body needs. So one way I sometimes draw this is to imagine that blood consists of two areas in terms of oxygen. So if oxygen is in the air here, the first part is the plasma. And that oxygen, when it enters the blood, it first dissolves in the plasma. You could imagine that plasma holds a little bit of oxygen. Sometimes I draw this with like some boxes, where you could imagine oxygen filling up those boxes. But there aren't very many. And if that was all that we had, that's all the oxygen we could hold. But fortunately for us, our blood, specifically our red blood cells, also contain, so this is the red blood cells, and those contain a lot of hemoglobin. So each of these circles is going to be a hemoglobin protein. And as we mentioned, each hemoglobin consists of 4 very similar subunits, and each of those contains one heme group. So there's 4 heme groups total in the hemoglobin protein. And each of those heme groups can carry one oxygen, one molecule of O2. So one hemoglobin can carry up to 4 oxygen molecules. So we could imagine you get the idea. So if we imagine that each of these boxes in the plasma could hold one oxygen, so that's, what, 6 right there? Now imagine each of these can hold an oxygen. So that's, let's see, 20 times 4, that's 80 of them right there. And that actually understates the difference here. Hemoglobin holds something like maybe 40 times as much oxygen as the plasma, maybe more. I'd have to check on that. But in any case, it holds a lot. So when oxygen enters our blood, it first dissolves into the plasma, and then from the plasma, it can enter the red blood cells and bind to hemoglobin. So that, and then when we need to get the oxygen out of the blood, it leaves the plasma to go to the tissue, and then can come off the hemoglobin into the plasma. So in the lungs, we're going to have oxygen coming in to the plasma, and then from there going to the hemoglobin. We'll talk about that that's just a concept, we'll get to the details. And then in the tissues, we're going to want the oxygen to come from the plasma, and then from the hemoglobin to the plasma. So it's transferring it in that direction. So the plasma is just sort of passing the oxygen to the hemoglobin, or taking it from. Our question then, though, we need to answer something else about hemoglobin, which is how much oxygen does the hemoglobin try to hold on to? And it kind of looks like we want that to change. In the lungs, we want the hemoglobin to be gathering oxygen. When oxygen comes into the plasma, we want the hemoglobin to be eagerly grabbing onto it. But in the tissues, as the oxygen is leaving the plasma, we want the hemoglobin to want to get rid of it, to surrender it to the plasma. So we have this interesting problem here. We want hemoglobin to change its eagerness to bind oxygen, what we would call its affinity. So hemoglobin, which I will usually abbreviate as HB, hemoglobin's affinity for oxygen needs to change so that in the lungs it can bind the oxygen, and in the tissues it can release the oxygen. Now, how we do that's a kind of an interesting trick. So that's a part of what we're going to be talking about right now. Okay, so let's talk about how hemoglobin can change its affinity for oxygen. Now, I'm redrawing the hemoglobin protein here in a little bit different of a way. So I'd recommend you drawing this yourself, draw each subunit as being sort of an eighth of the circle and give it a little lip here. This is going to be the heme group. But what I'm doing here, this heme group is partially hidden away from the outside world. It's relatively hard for oxygen to get to it. This is not, strictly speaking, an accurate way of drawing what's happening, but I think it will help a little. So, if we're thinking of the hemoglobin this way, we're going to start with it with no oxygen bound. But if we imagine there's some oxygen out here, and we imagine a little of that oxygen, even though it's relatively hard, getting in here and binding to one of these heme groups, the binding of oxygen to the iron changes the way the iron is sitting in the heme group, which then actually causes the whole protein to change shape a little bit. And it goes from looking like this to doing this. And now you can see that now those openings are a little bit bigger. It's a little bit easier for oxygen to get to the next heme groups. And as this happens, as more oxygen binds, it opens up even a little more. The first one seems to have the biggest effect. But even after that first one, as you bind a second, third, and fourth, the hemoglobin opens up more and is more eager to bind and hold on to more oxygen. So the question is, how likely is each of these to bind? And once the oxygen's on there, it's not permanently bound. But how well it stays bound will kind of depend on how opened up the hemoglobin is. The more open it is, the more it tends to hold on to the oxygen. So if we start with no oxygen, if we start with little oxygen, the chance of any oxygen getting in there and binding to it is relatively low. So go back to the way it was. If there's not much oxygen out here, the chance of an oxygen molecule getting to any one of these and encouraging that process is relatively low. Even if one does, and it opens this up a bit, if there's not a lot more oxygen to get in there and bind to another one, then the one that bound might come off before another one gets in and close the hemoglobin molecule back up. So imagine that you have a lot of these sitting around in some blood. And there's very little oxygen around in the plasma. The chance of an oxygen getting in here and binding and opening this up is small but not zero. And if one does, the chance of another one getting in to keep holding it open before the first one drops out is even lower. So for any given hemoglobin, there might be none bound to it, or one oxygen, or in a few cases maybe two, but very rarely 3 or 4. So if I took a picture of 100 hemoglobin molecules in that circumstance, and said, what's the average saturation of them? It would probably be low. Maybe the average might be 1, maybe 1 out of 4. On the other hand, if I add more oxygen to this, like a medium amount of oxygen, the chance of one of them getting in here and binding is greater. And when it does, this opens up, and before this one happens to come off, it's more likely that another one is going to come in, which will actually tend to open it up even a little more. Now, you might even get a third one in, and then maybe the first one drops out, but then maybe another one comes in. So if I look at my field of 100 hemoglobins, rather than seeing none or one or occasionally two oxygens on them, I'd see probably two, maybe three, occasionally one. So my average has gone up to something like 2.5 oxygens per hemoglobin. And if I add even more oxygen, then it's very likely that one will bind and open it up. And then before that one comes off, you'll get 2, 3, maybe even a fourth getting in there, because there's lots of oxygen able to come in and help hold this thing open. So then when I take my picture, there will be mostly 4, maybe occasionally 3. So my average is going to be 3+ per hemoglobin. What all of that means is that if I were to, I'm just going to sketch a graph here, and then I'm going to draw it bigger in a moment. If I were to make a graph of number of oxygen on the hemoglobin for each amount of oxygen in the plasma, if oxygen in the plasma is low, then I probably won't have very many I probably will not have a lot of hemoglobins on the oxygens on the hemoglobin. But as I increase the plasma, once I get a few of them bound on there, suddenly, once it starts opening up, it becomes much more eager to bind. My rate increases up towards a maximum. And eventually you can't get any more because we're approaching 4. So you get what we call a sigmoid curve. Sigmoid just means S-shaped, where we start low and then have a rapid acceleration with the number of oxygens bound, and then it levels off. This coming from, as you get that first 1 and occasionally 2 on there, it really opens up the hemoglobin for more oxygen to bind. So rather than just having more plasma means more hemoglobin, just a line, we have a sigmoid, where more plasma suddenly increases the amount of oxygen that can bind to the hemoglobin. Now that also means that as I decrease the plasma O2, the hemoglobin will go from mostly full of oxygen to suddenly dropping off a lot of oxygen. Suddenly it's going to change to releasing oxygen more easily as you take oxygen away from the area around it. That's going to end up being very important. What we're building here is something called a hemoglobin-oxygen dissociation curve. And that's where we're going to go next. All right, so based on what we just saw, now we're going to put together that oxygen hemoglobin dissociation curve. So oxygen hemoglobin dissociation curve. Some of that is probably in the glare right now, so I'll try to put something on the video which actually has the better spelling. Now, this graph is on this side is we're going to label this as hemoglobin saturation. In other words, what percentage of the oxygens on the hemoglobin are currently have an oxygen on them? This is easiest to imagine if you think of 25 hemoglobins, so that there are a total of, since there's 4 per hemoglobin, 25 times 4 is 100. There's 100 iron atoms available. How many of them have an oxygen bound at any given moment? So 100% saturation would be when all of the hemoglobin sites have oxygens. All of those are full. 75% saturation would be when 3 of them are full. 50% would be 2, 25% meaning 1, and 0% meaning none. Now, that doesn't mean that for all 25 hemoglobins, you've got either 4, 3, 2, 1, or nothing. You could have a situation where 10 of them have 4, 5 of them have 3, and a couple of, you get any group you want. It's just the average number, the on average, how much is the hemoglobin saturated. And by the way, when you take a pulse oximeter reading and you read hemoglobin saturation, this is what you're reading. So, down here on this axis, we're going to have the plasma PO2. And that's going to range from 0 I'm going to have it go up to 120, although there's technically no upper limit. You could keep stuffing oxygen in the plasma if you have enough high pressure oxygen outside of it. And if you remember in one of the previous lectures when we talked about the oxygenation of blood, arterial blood, systemic arterial blood that's oxygen rich, should have a plasma PO2 of about 100 if you're at sea level, whereas systemic venous blood, deoxygenated blood, should have a plasma PO2 of around 40. So, let's go through what we know. In arterial blood, if you've got a plasma PO2 of about 100, your hemoglobin is highly saturated. If you know about this in clinical, you know that on a pulse ox, which is reading arterial hemoglobin saturation, you should be seeing values 95 plus. So this would probably be somewhere around 98%. So I'm going to, here at 100, I'm going to go up here to about 98% saturated. Now, in our systemic venous blood, which has had oxygen taken by the tissues, we have a plasma PO2 of about 40. Interestingly, that has a hemoglobin saturation of somewhere around 75%, which is very surprising to a lot of people. We look at this and say, are you telling me that in my deoxygenated blood, my hemoglobin, on average, still has 3 of its 4 spots filled by oxygen? It's still 75% full? Yes. This is sort of like saying, in my car, I consider myself to be degassed, low on gasoline, when my tank is still 3/4 full. It's kind of an interesting thing, but in the kind of blood you would get coming back from a hard-working muscle, though, where, for example, your plasma PO2 might be 20, the hemoglobin saturation at that point is closer to 30%. So if we were to fill in the gaps on this curve, you'd get something like this. There's our sigmoid S-shaped curve, where saturation starts low, but then as you start to get at least one oxygen on there, suddenly we have a rapid increase, followed by leveling off as we're getting 3 to 4 oxygens on there. And by the time we get to a plasma PO2 of 100, we're at 98% full. Virtually all of the hemoglobin is stuffed as full of oxygen as it can get. That does mean that your systemic arterial blood is holding almost all the oxygen it can. The hemoglobin is effectively completely saturated. You couldn't put a lot more oxygen in there, and the plasma can't hold that much. So it's hard to get a lot more oxygen into your arterial blood without doing some strange things about breathing very high pressure oxygen. So this is the dissociation curve for typical hemoglobin under normal conditions. We're going to talk about some things that change that. But first, let me talk about how what you do with this graph. So if I were to ask the question, how many oxygens does my hemoglobin tend to give up when I go from systemic arterial to systemic venous blood? That might be a good test question, or something like it. I can answer that question with this curve. So, if my question is, how many oxygen molecules does hemoglobin give up on average between systemic arterial and systemic venous blood? In other words, as my blood goes from the systemic arteries through the capillaries and ends up in the systemic veins, how much oxygen does the hemoglobin tend to give up to the tissue, to the blood and then to the tissues? My systemic arterial blood has a PO2 of about 100, which puts me at 98% saturation. In other words, my hemoglobin tends to have about 4 oxygen on it. My systemic venous blood has a saturation of more like 75%. If you're 75% saturated, you're 3/4 saturated. So how many oxygen is the hemoglobin holding? Well, its maximum is 4. What's 75% of 4? 3. So this is holding 3 oxygen. This is holding about 4 oxygen. So if I've gone from having 4 on each hemoglobin to 3, how many have I given up? 1. So when if I'm at rest and my systemic arterial blood is a PO2 of 100 and my venous blood is a PO2 of 40, my hemoglobin on average has given up 1 out of its 4 oxygens to the tissue. So sometimes the question then comes up, why do we keep so much there? Well, think about this. Let's say I decide to go for a jog. So now my skeletal muscle is using a lot more oxygen, meaning that the PO2 of the blood plasma, as it goes through that skeletal muscle, is going to drop more. It drops to 40 if that's the PO2 of the tissue. But if the PO2 of the tissue is 20, then the plasma will drop to a PO2 of 20 as well, as it reaches equilibrium in those capillaries. And as plasma drops from PO2 to 20, notice what happens to the hemoglobin saturation. We go from 4 in the systemic arterial blood to something more like 30% saturated here. 30% saturation is something like 1.1 oxygens per hemoglobin. 30% of 4. 1.2 actually, I think. So on average, if I'm talking about how much oxygen does my blood give up when it's going around skeletal muscle that's in use, which has a lower PO2, I might go from 4 in the systemic arterial blood to 1.2 oxygen per hemoglobin in the venous blood coming away from the muscles. In other words, my hemoglobin gave up, on average, 2.8 oxygens. Almost 3 times what it gave up here, where it just gave up 1. That's kind of interesting. The fact that the hemoglobin affinity drops off so dramatically here between as we go from at-rest tissue to hard-at-work tissue is not coincidental. This is part of evolution. Our hemoglobin is set up to rapidly start releasing oxygen as I get into tissue that needs it more, which is handy for us. Okay, a couple of more things about this. First, let's talk about what the effect of pH on this is, because hemoglobin is going to respond to oxygen differently when the pH changes, as it turns out. If pH becomes more acidic, this curve tends to shift to the right. And here's what that looks like. So if I look at this under a slightly more acidic pH, up here toward the top, it's not very different. So this is lower pH. Up here at the top, it's not all that different. Down here at the bottom, it's not all that different. But here in the middle, because the curve has shifted over this way, notice what happens to the hemoglobin saturation at each plasma PO2. So here, at a plasma PO2 of 100, it's not all that different. Maybe we've dropped to 95%. Here, though, at a PO2 of 40, it's dropped noticeably. This looks like it might be down around, let's see, 50, 60, 70. That's probably something like 68% saturated. So it's now 10% less saturated than it was. And down here, it's even more dramatic. At a PO2 of 20, looks like maybe I'm down around maybe 18%. So as the pH gets more acidic, the hemoglobin saturation tends to drop. It tends to hold less oxygen. And again, right at first that might seem counterintuitive, but let's think about when that would happen. What kind of things are going to drop the pH of my blood? One of them would be if my muscles have to shift over to more anaerobic metabolism and start producing more lactic acid. In that case, as my blood becomes more acidic, the hemoglobin, while it's still holding up pretty close to its full amount of oxygen in the arteries, starts to become more able to give up oxygen. Rather than holding on to 3 out of its 4, it holds on to a little less than that. And especially around muscle, it holds on to even less than that, so it surrenders more oxygen. That actually helps to deliver more oxygen to your tissues, which is kind of handy. So, I also wanted to illustrate one of these more Dr. Luguber type strange ideas to you. So let me get rid of the low pH curve. And instead, give us a situation where Dr. Luguber has decided that he wants to make blood he wants to make hemoglobin which is selfish, like he is. He's a very selfish person. So his hemoglobin, he says, why would I ever want my hemoglobin not to hold on to as much oxygen as possible? Isn't oxygen good for me? So what he does is make hemoglobin whose curve looks like this. Stays at 98% at all plasma PO2s. So Dr. Luguber's new hemoglobin retains a 98% affinity for oxygen at all plasma PO2s. How well is that going to work? Will it work in the lungs, and will it work in the tissue? So, think about that for a moment. Now, in the lungs, where there's lots of oxygen available, the oxygen from the air is dissolving into the plasma PO2 is 100, his hemoglobin will be at 98% saturation. It's eagerly binding up that oxygen from the air. Yay, everything's great. But what happens when it gets to the tissues? That blood comes to the tissues, oxygen starts going from the plasma to the tissues, and the plasma PO2 drops to 40. Regular hemoglobin drops its saturation to 75%, so it starts giving up oxygen. But his hemoglobin stays at 98% affinity. So that oxygen stays bound to the hemoglobin, and his hemoglobin gives up no oxygen at all. Thus, delivers no oxygen to the tissue, thus his tissue dies of hypoxia, because his hemoglobin is useless. It just holds on to the oxygen all the time. I hope that makes sense. Now, we should take a moment here to talk about some other things that can affect this. You see here that pH can affect the binding of oxygen. pH can affect the binding of oxygen to hemoglobin. It does it in what we call a non-competitive way. The pH changes the shape of the hemoglobin, which reduces its affinity a little bit. But we can also talk about a competitive binder. The most common one we talk about is carbon monoxide. Carbon monoxide is a gas which has no odor, it's colorless, you can't really see it or smell it. It's produced when things don't burn completely. You get it anytime you're burning something in a realistic environment, you'll get a little bit of carbon monoxide. But things that smolder tend to produce a lot more. So if your furnace isn't working properly, or if you're smoking, you tend to get more carbon monoxide. Carbon monoxide binds to the iron in the heme group. But heme has about 250 times more affinity for carbon monoxide than oxygen. In other words, if hemoglobin can bind to either oxygen or carbon monoxide, it will bind to the carbon monoxide. In fact, if there's an oxygen on it, it will kick the oxygen off and take the carbon monoxide instead. And the carbon monoxide doesn't let go. So once that iron atom grabs a carbon monoxide, it can't bind to oxygen anymore, and it won't let go of that carbon monoxide, meaning that it's useless now. That particular iron atom is no longer available for oxygen. That reduces how much oxygen the person's blood can carry by a lot. So if you get a lot of carbon monoxide into your blood, it binds to all the hemoglobin, and now you can't carry any oxygen. And there can be oxygen in the air, but since your blood can't carry it on the hemoglobin, you can't use it very well. And you can actually die of hypoxia even when there's plenty of oxygen around because all of your hemoglobin is occupied. It's a good reason not to smoke. because heavy smoking generates carbon monoxide, and it can actually impair your body's ability to carry oxygen. Now, carbon dioxide also binds to hemoglobin, but it doesn't bind to the oxygen. It binds elsewhere on the protein, and it actually does change the shape of the protein a little bit. It's actually similar to acid, that it shifts the hemoglobin curve a little bit over, so when there's carbon monoxide present, it makes the hemoglobin give up a little more oxygen, which is actually handy. If you think about it in the tissues, not only are we giving oxygen, we're taking carbon dioxide, and as that carbon dioxide comes in, and some of it sticks to the hemoglobin, not all, we'll get to that, the hemoglobin gives up even a little more oxygen, which is handy. So our next thing we're going to talk about is how carbon dioxide is carried in the blood, and what that does with hemoglobin, and some other aspects of that. So we'll get to that in just a moment. Wait, I forgot something. I forgot to mention, I wanted to give you a statistic here about how much oxygen hemoglobin carries, how much good it does for us. So, 1 liter of whole blood, let's write this on here. 1 liter of blood can carry about 200 milliliters of oxygen. So if I've got a liter of blood, I can bind about 200 milliliters of oxygen to that blood. Of that, about 3 milliliters is in the plasma. The plasma can hold about 3 milliliters of oxygen. The hemoglobin holds about 197 of it. So the hemoglobin's capacity for carrying oxygen is enormous. It carries vastly more than the plasma alone can carry, which is very helpful for us. One way of thinking of how this works, an analogy I sometimes use, is to imagine that you and your little sibling are around Halloween, if you celebrate Halloween. In any case, something involving candy. So imagine that you and your little sibling are going to the candy store, and you have a big sack for carrying candy, and your little sibling has a small sack for carrying candy. Now, you are far too cool to be seen getting excited about getting candy from the shelves in the store. But your little sibling is not. However, you are not too cool to take candy from your little sibling. So what we imagine now is your little sibling going through the store and saying, "Ooh, candy!" And they start taking candy from the shelf and putting it in their bag. And their bag fills up. And as their bag is full, they say, "Oh, I guess I'm done." You, though, say, when they're not looking, you take some candy from their bag and put it in your bigger bag. And they look and say, "There's more room in my bag!" And they go back to the shelves and they put more candy in it. And you look at their bag and say, "Hey, look over there." And you take some candy from it. And they say, "There's more room in my bag! It's a magic bag! It's fantastic!" And they go get more candy. So what you end up with is, you are willing to take candy from your sibling as they get more candy in their bag. As their candy level rises, you're willing to take more, which leaves more room in their bag. So then they just keep taking candy off the shelves and you keep taking it from them, and you can take a lot of candy that way. You end up with a full big bag and they end up with a full tiny bag. That's a little bit like what happens in the lungs. So if your little sibling is the plasma with a very limited ability to carry oxygen, but you are the hemoglobin, can carry a lot more, think about what happens. You go to the candy store, the lungs, there's lots of candy, oxygen, around, and your little sibling, the plasma, starts taking oxygen in. The plasma fills up quickly, it can't hold very much, but you, the hemoglobin, as the plasma PO2 goes up, your affinity for hemoglobin, your eagerness to have some, rises. You start taking some from the plasma, binding it to you, and once it's bound to the hemoglobin, it doesn't count as being dissolved in the plasma anymore. So, as you take it, now there's more room in the plasma to bring more in from the air. And then as it comes in, you bring it in, and there more comes in from the air. So the plasma is just a conduit, and your eagerness to take it from there depends on how much is in the plasma. You keep doing that until the plasma reaches equilibrium with the air outside, and you, big bag, are 98% full, having kept taking it from their little bag, until now you're both full. Their bag is full and your bag is full. Now when you get to the tissues, on the Halloween night, your little sibling goes out and gives candy to the homeless. They start going out and giving candy from their bag. And their bag starts to empty. They won't be able to give very much, but you, following around them with the big bag, see them emptying their bag and want them to continue doing this good deed. As their bag gets less full, the plasma O2 drops, your willingness to let go, you don't want to hold as much candy, so you start putting some back in their bag, which they can then pass on to homeless individuals. And as their bag keeps dropping, you keep filling their bag from yours, and they keep passing it on until your bag, somewhere in here, depending on how much you're trying to give away, is mostly empty, and their bag is partially empty. And now you're back at equilibrium. That's kind of a strange way of looking at it, but that's one way to think about how oxygen transport is working in the blood. It comes into the plasma and then binds to the hemoglobin, and now it doesn't count as being dissolved anymore, so more can fit into the plasma. Hopefully that helps a little.